everyone, this is Dr. Shirisha, working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to review Module 5 question bank, right? So here we are going to discuss broadly what type of questions you can get in your mids as well as your externals. As I'm talking about module 5, so what a binary search tree is, AVL trees, MV trees, and hashing concepts we are going to see. So coming to the basic taxonomy of trees. So they might ask you the taxonomy of trees and explain. So starting from the general trees, putting a constraint on general trees that it can have a max of only 2 children. So binary trees, then again putting constraints on a binary tree, that is you can construct heap trees and binary search trees. Okay, so important question over here is what a binary search tree is. Any tree, only binary tree, let me make it simple, binary tree, if you put a constraint saying that the value in the left children have a value which is less than or equal to its parent, whereas the right have a value greater than its parent, we call it as binary search trees. Okay, so the major applications of binary search tree is a representation of arithmetic expressions, and in order, guys, very important, in order traversal of a BST gives you ascending order data. Okay, so please remember this one. And Unix, in the Unix kernels will be implemented. In Unix kernel, virtual memory is implemented using BSTs, binary search trees. Okay, then coming to the operations that we can perform. On any tree, we can perform 3 major operations. One is search, insertion, and deletion. And the time complexities in case of binary search tree is order of log n each. Okay, coming to the insertion, there is very important one. Either they can ask you to write an algorithm to perform insertion operation in a binary search tree, or they may give you a list of elements and they might ask you to do the same. If they ask you to write an algorithm, please put the statements stepwise. Okay, start with creating a node, just like as I have mentioned over here. Okay, so remember one thing, in case of binary search trees, always a newly inserted element will settle as a leaf node. Remember that point, guys. Okay, so this is the algorithm. If they give you a list, something like this, and ask you to construct, so keeping the first element as the root and comparing the remaining elements with the roots and its children, grandchildren, and check whether where the new node is going to settle, right? So next element is 15. As it is less than 25, it will go as the left child. 50, as it is greater than the root, it will go as the right child. Remember, when you work with trees, we have the address of only the root node. So if you want to search, delete, or insert, you have to start with the root node, comparison with the root node only. Next 10, compare it with 25, as it is less, go to the left side, compare it with 15, go to the left side. Okay, so here it is, 10 is inserted. Next element is 22. It is less, 22 is less than 15 but greater than 25, so it goes as the right child. Okay, then comes 35. 35 is greater than 25, so it goes to the right hand side. Compare it with 50, lesser, so goes to the left hand side. Right? So very simple, guys. You might have seen whatever the element I'm inserting, it is getting and settled as, being settled as the leaf node. Right? Very good. So the next element is 70. So the rightmost element, next 4, 12, 18, 24, 31, 44, 66, and 90. Right? So this is how a binary search tree is constructed. Okay, so deletions. Deletion is also very important question, guys. They might ask you the algorithm or they give you a list of elements. The most famous question is they'll give you a list of elements and ask to construct a BST and delete a set of elements they'll give and they'll ask you to delete them. Okay, so for that, to answer such questions, you must be able to create it. You must know how to create it and then what are the cases that are involved in deletion. Basically, there are three cases, my dear. The first case is if the element is a leaf node. If the node which you want to delete is a leaf node, no problem, delete it. It will not shatter the BST. Very good. I removed 7, nothing ill happened, right? What if you try to remove a node with a single child? If you try to remove a node with a single child, before removing, you have to build a relation between its child and parent. That is, if you want to delete 10 over here, build a relation between 8 and 14, right? So now the coming to the remaining part of 14, that is the subtree 14, it will be as it is. It will not change. Okay. So this is how we are going to do. For example, if I want to remove 6 over here, how to remove that? So as its parent is 3, build a relation between 3 and 4. Okay, and remove 6. Nothing is going to happen. You are not going to lose the data even after removal of a node. Okay, remember guys, after every insertion we have seen that the resultant tree is a binary search tree. The same rule applies for deletion also. After every deletion, the resultant tree must be a BST, binary search tree. Okay. The third case, this is a tough case, a case where you are trying to remove a node with 2 children. So you have 2 options over here, right? The option is replace the node which you want to delete with its successor or predecessor. Successor is the leftmost element of its right subtree. Predecessor is the rightmost elements of its left subtree. Either one of the elements you can do that. So for example, in this tree, if you want to remove 3, so the successor of 3 is that is in its left tree, the rightmost element is 1. In the left subtree, rightmost element is 1. In its right subtree, the leftmost element is 4. So you can replace it either with 1 or 4. So here I have chosen 4 and I have replaced it. So if I bluntly remove 3, I'm going to lose huge data, right? I'm going to lose this data. So to overcome that, I have to build a relation. So simply if you want to remember, as I said, the infix expression, the infix traversal of a binary search tree will give you ascending order data. So if you write the ascending order of the tree, then use the left hand side element or the right hand side element which you want to delete, replace with that. It is a simple trick. Okay. Next, for example, here I want to remove the root itself. If I want to remove the root itself, then I either in the left subtree the rightmost element, that is 7. With 7 I can replace, or with the on the right side the leftmost element which is 10. With the 10 I can replace either one of them. Okay, so I have chosen predecessor now and I have replaced it with 7. Okay, so that is a binary search tree. Coming to balanced search tree, an extension of that. Balanced search trees are also binary search trees with an extension of balance factor. So why we have come to balanced search trees or AVL trees? Guys, in exam point of view, please be very clear. They may ask you with either one of the terminology. They may term it as balanced search or AVL. Both are one and the same. Okay. So why we have come to balanced search tree is if the list given to you is in ascending or descending order, then your list, the binary search tree which you construct will be either a left skewed or right skewed. That is overweight in one side only. To overcome that, it will raise the number of levels. That's it, right? It will increase the height of the tree. To overcome that, we go for AVL trees where the all insertion, deletion, both the operations belong are based upon balance factors. Balance factor is nothing but the difference between the height of left subtree and the right subtree. Okay, for each and every node we have to calculate it, right? So using that we can do. So if any node gets violates these rules, that its balance factor is neither -1 nor 0 or 1, we rotate it. How we rotate it? Two types of rotations. Very, very important question in exam point of view. Explain the rotation concept in AVL trees. Single rotation, double rotation. Whenever you get this question, please explain with an example. See, I have taken these three nodes and I have explained a left and right rotation, that is single rotations. Okay, so with simple three nodes, you explain it. Okay, whether it is single rotation or double rotation. Okay, explain with diagrams. If they give a list of elements and they ask you to construct an AVL tree, so at each, you have to draw a separate binary balanced search tree at each and every insertion. Please do not draw a single tree which is balanced one. Very good. Please do not do that. You will not get the marks. Right? So in the scheme of evaluation, each and every step carries certain marks. So which must be justified by you. Okay, so first 63. As this is the first element, no left or right children, balance factor will be 0. Next, insert 9. So once I insert 9, 0, the balance factor of 9, as it is a leaf node, it is 0, and 63, it is 1. Right? So next, insertion of 19. So as I inserted 19, the root node lost its balance. It is 2, its balance factor. So why it lost balance? Because of in its left subtree you have inserted an element in the right. So left right rotation you have to adopt. Please mention this left right rotation, guys. Be confident. So to understand this concept more keenly or in depth, please follow the channel. A separate lecture video is presented where we have given a demo on the same with few examples, right? How, why, and all, right? So that's what. Go through that and specify. Just don't rotate it and tell that, yeah, it's balanced enough. Don't do that. Okay. So left right rotation. In left right, first left rotation, then right rotation. This is the diagram of intermediate result. You have to show that also. This is the result after right rotation. LR rotation is a set of two rotations, left and right. What you are going to move? Left, which is the element 9. Then a right of 63. That you have to mention. Very clear. Next, insertion of 27. Next, 18. Balance factors are fine. Next, 108. Balance factors are fine. 99. Balance factors are fine. 81. See, 108, 63 and 19. Three elements lost their balance because of insertion of 81. You have to look for the nearest element which lost its balance, which is his grandparent. If you go for the relations, so 108 becomes its grandparent, 93 grandparent, 19 is the boss, right? So who is the nearest relative who got affected? His grandparent. So have a look. Why 81, in point of view of 81, why my grandparent lost its balance? Because of me, where I was inserted in the left subtree as a left child. So go for right rotation. And looking at the picture itself, you can understand very clearly, guys. See, coming to 108, all the two elements are in its left side. There is no element on its right. Don't you feel that it is imbalanced? Right? Balance it. See, I have rotated 108 towards right and 99 went as the root. A single step rectified the balance factor of its grandparent and the root. Right? So this is, see, if they give you a list of elements and they ask you, please, after each and every insertion, write the balance factors. If any node gets imbalanced, please mention because of what it got imbalanced and what the corrective rotation technique which you are going to adopt. Take it, implement it, and show it. If it is double rotation, you are going to perform 2 rotations. Show the intermediate result also to get full marks. Right? So, what about deletion in AVL trees? Deletion is AVL trees is as it is as BSTs, but only thing is after every deletion, calculate the balance factors. If any node loses its balance, adopt one of the techniques and perform the rotation. Okay, for example, in this tree, what if I remove 81? No problem. Balance factors are fine. If I remove 27 in this tree, 63 got imbalanced. Negative value. Negative value itself tells you that it is heavier on its right side. So go for left rotation. Okay. Then again delete 18 from this tree. If I remove the root got imbalanced, even that is negative. That is your right side is heavy. Rotate towards left. Right? So this is how we are going to rotate the things. Coming to the applications of AVL tree. So the basic drawback of AVL trees is if the insertions or deletions are high, with every insertion and deletion, you have to calculate the balance factors of all the nodes. From the root till the leaves, you have to calculate, which is a very time-consuming process. That is the major disadvantage with AVL trees. Otherwise, it is the best one. Time-consuming process. So the applications goes with the disadvantage. Are cases where the tree which you construct is a standard one. Rarely you go for insertion or deletion. It is mainly meant for searching. Then AVL is the best one. This design is best one. That is, it has very short search time because number of levels will be very less. So, and the input data is sorted or nearly sorted. Okay, sorted in nature. So, okay, and to overcome the drawback of AVL trees, that is time consuming for insertion and deletion, red black trees have come into the picture, which goes a very high way, which goes beyond your academics right now. But for your understanding, I have presented over here. Okay, so M-way search trees. So whether it is a tree, binary tree, binary search tree, or an AVL tree, we have seen that every node have single element, right? Not more than one element, right? So why only single element? If the number of the data set is high, even if you adopt AVL tree, the number of levels will be high. So to reduce the number of levels, they have come up with M-way search trees where multiple keys will be present in a single node, right? And the properties are like this. Have a look at this one. M-way search tree of order 8 will have 8 children. Order specifies number of children. So, and if it is order n minus 1 number of keys you can have. So the properties with the keys is the keys must be in ascending order. Okay, the keys are in ascending order. And coming to the property of keys in its children, so all the keys left, all the children left to a key must have a lesser value, and all the children right to key must have a value greater than the key. Okay, so BST property. Inherently, you can see that BST property is prevailing with multiple keys in a single node. Okay, So B trees is a self-balanced one. It is a generic form of multi-way search trees with few properties, and the set of properties of B trees of order M is very important. So one point it says is all leaves must be at the same level. That is a very important property, and with every insertion and deletion you have to take care of that. Second property is all the nodes except the root must have at least m by 2 minus 1 keys and a maximum of m minus 1 keys. As it is order m minus 1 keys. That is the actual funda. Okay. So similarly, few more properties which you need to take care of. So basic applications of B trees. So wherever the number of reads are there, use it because it reduces the time of reading. If the database is large, this is the best choice. So for handling databases and file systems, handling bulk amount of data, we use B trees. Okay. Coming to have a look at a small example of B tree of order 4. If you look at this one, all the okay, the center subtree, it is, you can call it as a right subtree of 30 or left subtree of 70. Both are one and the same. Have a look. All the elements are greater than 30. That's why it is right subtree of 30. All the elements are less than 70. So it is left subtree of 70. Okay. So what are the operations? As I said, search, insertion, deletion are the basic operations that you can perform with the complexity of log. Okay. So, and the algorithms which are very much important in exam, rather than algorithms in AVL trees and AVL trees and the B trees, they go for problems, my dear. They give you a set of elements and they'll ask you to construct, or they'll give you a tree and they'll ask you to insert and perform few deletion operations. Okay, so have a look at how to construct this one. So this is a random list of elements I have taken. So 5 it is, and I said please remember this point, all the leaves must be at the same level, and the keys within a node must be in ascending order. So next 3, when I am going to insert 3, please see that I cannot write it over here. I cannot store it like this. The keys must be in ascending order. So shift 5 and give a slot for 3. Next 21, it is in order. Now 9. As the node cannot accommodate, push the middle element and make it as the root. So see, BST property existing or not. All the elements which are left to 9 are lesser than 9, and the element which is right to 9 is greater than 9. Okay, now I inserted 1. Have a look. 3 and 5 are there. A slot is present, and I am not going to place 1 over here. I'm going to shift 3 and 5 and make a place vacant for 1, and I'm going to insert because I want the keys to be in ascending order. That is the key property of B trees, guys. Okay, then next insertion of 13. See, I have moved 21 and inserted 13. What if I want to insert 2? As per the order, or as it is supposed to be in ascending, 2 is must have a slot on the left hand side of 9, right? But it cannot accommodate. Push its middle element to the top, which is 3. So when you push 3 to the top, see, 9 must be shifted and given, it must give a place to 3 because 3 is less than 9. Sorry, yes, right, 3 is less than 9. So have a look at this one. Even here BST property prevails. All the elements left to 3 are less than 3. Right is greater than 3. In view of 9, element left of 9 is lesser. Right of 9 are higher. Right? So if I insert 7, very good. As if when I try to insert 7, its value is between you. We have always insertions in a tree, we start from the root. It is between 3 and 9. So I am going to travel to the between subtree. Okay. Then one more element, then 12. If I try to insert 12, the right side of 9 cannot accommodate. So push the mid element to the top. 13 will be sent to the top. Now split it. Okay. So again, one more insertion of 4, which is accommodated as the right child of 3. Then insertion of 8 as the mid node, that is the right of 3 cannot accommodate, it will push 7 to the top. Even root cannot accommodate, it will push its mid 9 to the top. So the final picture will be 9's left and right, 3, 7, 13 respectively. Left of 3, right of 3, right of 7, left of 13, right of 13. So this is the final B tree which I have constructed using NS. Okay. So the next one, how to delete. Deletion is a very important one. As I said, they might give you a tree something like this and they'll ask you to remove. What if they ask you to remove 65? Push 70. Very simple. So push 70 to the top and the BST property prevails. What if you remove 70? Merge them. Right? Next 80. Next deletion of the 100, right? So when you remove 80 also, 60 will have only one right child, which is 90. So this is the deletion. Last concept is hashing. Hashing is nothing but constructing a table to store the keys for huge values, unique keys for the huge values, right? Using hash functions, by feeding the large value to the hash function, we are going to make it short a key which is going to unlock the huge value, right? So these hash functions will help me out for the same, and hash tables are used to store for it. Okay, this hash functions property must be they must be easy to compute, evenly distribute, and minimize collisions, right? So ideally, if you take hash function must give you a key such that every insertion, deletion, search operation complexity is 1, which is next to impossible in the real time. Okay, so the hash functions are classified into static and dynamic. Static is the set of keys are fixed, the same old funda, keep on repeatedly using the same. Static. Dynamic, the keys will change. So you have to dynamically change your funda also. So these are a few types of hashing. First one is direct. If your value size is less, then use that data itself as a key. But if the values are high, lengthier in nature, then it is a problem. So, okay, direct method is not convenient. So, modular division. Using a prime number, do modular division and get the key. So, hash function is defined as key mod n. You'll get the value. You'll get it. Next is square and get the mid value. If 3121 is the value, square it, you will get this value 9740641. Take mid of it, 406. Use it as a key. Or you can even subtract a constant. Subtracting you can use. Folding you can use. If you have a large key, 4, 5, 6, break it into pieces of 3, add them. Why 3? Address size. It is the address size. If your address size is 4, break them into 4. Right? Reverse folding also you can do. 1, 2, 3. Reverse the intermediate ones, add them and get the address. Even that you can do. Pseudo random also you can do. Y is equal to ax plus c, where a and c are constants. Even that you can do. There are many techniques, types of hashes. Okay, but the main point is hash collision. Very, very, very important one in exam point of view. Hashing, types of hashing is one important question which we have seen just now. Next, they'll ask you what is collision in hashing. Have a look at this picture. Please draw a diagram to explain the same in exams. Okay. So key 1 will give you block 4. Very good. Key 2 will give you block 3. Very good. Key 3, block 1. Key 4, block 2. again key 5 is colliding with block 1. So both the keys are key 3 and 5 are looking at the address block 1, which is a collision, right? So how to overcome that? Two types of techniques are there: separate chaining and open addressing, right? So what is separate chaining? Very simple one, but highly it's efficient one, but highly costly one, I can say. Simple to implement. It is a point of chain. See, as I said, block 3 and block 5 are at a point of collision. Then make their addresses as a chain. What is there in that? But it is less sensitive to hash functions. It doesn't much rely on hash function. Okay. So, and the number of collisions will literally reduce to zero, because if you find a collision, create a node, append it, right? But the drawback is the amount of space it takes. Okay, that is the worst. And few blocks will never be used, and few will be continuously used, raising to a huge length, increasing the length of the chain. So if you are choosing a hash function, it went wrong, then the chain will raise, making a few blocks to go under starvation, right? So have a look at this one. So to store, and my function is key mod 7. You will get problems, guys. Main thing with the hashing is you will get problems like this. Key set of keys will be given and a function, or they'll ask you to take a function and perform. Okay. So pictorially you have to do that. So my empty table. So to insert 50 mod 7, module answer is 1. So I stored at block 1. Next is 700 mod 7. 0, I have stored at index 0. 76, 86, I have stored at index value 6. Then comes 85. Even 85 mod 7 is 1. At index value 50, all 150 is already there. So make a chain. Link. Even 92 will give you index value 1. So another link to that. 73, index value is 3. Fine. 101, even 101 have an index value. So that is the result is 3, which refers to the index value 3. So already 73 is present. Make a chain. Have a look. See, 3 different chains are there, which needs, these nodes need addresses to store the next node. But here 3 cells are there which are under starvation. They are not being filled. That is the drawbacks of separate chaining, which you can overcome using open addressing. The advantage with open addressing is it is not going to use any extra space. It will work out with the space which it has in its hands. First one is, there are 3 types: linear, quadratic and double. Okay, so in linear probing, very simple. If you find a cell or a block is already filled, collision occurred, go to the very consecutive cell and fill the data. That is linear probing. Have a look. See, the story is fine till you reach here, 85. It gets collide with 1, index value 1. As it is already filled with 50, send it to the next cell. So it went to index value 2 and it sat over there. Coming to 92, even it had a collision. Its reminder value is 1. 50 is present. Go to the next cell. Even that is fill. Go to the next one and fill. Right? Next slot and fill. So this is how you can see. Have a look. All the cells are uniformly filled without using any extra space. But the drawback with linear probing is searching is difficult. To search an element, what you're going to do, you're going to use the same old hash function, right? If you use same old hash function and collision occurs, you keep on searching for a linear search. Searching in consecutive locations is nothing but a linear search, right? So you will go into a trap of linear search if the list is high. So to overcome that, you can go for quadratic probing. So quadratic probing, very important in exam point of view, guys. They'll give you problems on it. Okay. Previously you had key, hash of key, mod n. Now you are going to use plus I square. where I value runs from 0, 1, 2, so on. You can extend it to any value, I value. Okay, why we use is initially with 0 only, go for the straight value of hash of key mod n, where n is generally the size of the hash table, size of the hash table. If you find a collision, change 0 with 1, 1 square. If you still find a collision, 2 square, collision 3 square, you can extend it to any length. Another solution for this is double hashing. In quadratic hashing, we had a single hash function. There we were changing the values of the variable I. Here we have two functions. One is the primary and the other is secondary. First of all, calculate with primary function. If collision occurs, go for the second hash function, which is an alternate. Okay, so this is double hashing. So guys, in exam point of view, what is hashing? Explain is the important question. Second one is what is collision? Okay. Third one, the most important, is collision resolution techniques. Okay, if they broadly ask you what are collision resolution techniques, draw a chart, explain each one of them. If they specifically ask what is separate chaining or open addressing, explain them with an example. Okay, guys, you are the one who is going to judge. Depending upon the marks, please choose how appropriately you can address this solution or answer it. Okay, so with this note, I would like to conclude. I hope this video was helpful for you to answer the questions and to go deep into each and every technique in hashing and the trees and all. Please do watch our lecture videos. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.